I'm going to start working on the ping code for the probe. I'll show you my network testbed that I'm using to test the probe. I'll use VSCode and PyMakr to get some initial Wi-Fi connectivity and measure the ICMP pings. Then I'll check that the accuracy of the ping timings is good enough to get a reliable number for measuring the network bandwidth and latency. Okay, for testing out my esp32 and the pinging from it and make sure the timings are accurate. So I'm going to do the following. So basically my development environment and the machines are set up like this. I have a PC and that has VSCode and PyMakr on it. That's where I'll be doing my coding, and then I've got a COM port connection to my esp32. And that's where the micropython compiler exists, and all the network traffic will be coming out of the esp32. I'm using my guest network at home to connect up to a router. And then that router is on my local area network, which is all 1 gigabit. And I've put one machine out there, so I've actually put another PC, which is a Win7 PC. It's at address 192.168.1.29. What I put on there is a thing called NEWT, and that came out of Microsoft's research labs probably about 10 years ago, but it's a network emulator. It works pretty well. Unfortunately, it only works for Windows up to Windows 7. It stopped working on Windows 10. So I've put NEWT on this machine, and that allows me to emulate different network latencies and bandwidths. It allows you to do a whole lot more, but those are the things I'll be interested in for testing out the ping times, or the ICMP round trip times, from the esp32 up to the Windows 7 machine. First thing I want to do is check that my VSCode and PyMakr development environment's working. So you see here I'm in VSCode. I'm using the REPL console to check whether OS is installed. It's not. So I'm going to create a new file in my probe directory called boot.py. So this is the first one that gets executed every time the esp32 starts up. And in that I'm going to put an import of the OS library. So what this should do is make OS available every time I'm in the esp32. So I've uploaded it. It also does a reboot on the esp32. You see now that OS is defined, and I can do an OS command, OS list directory, and that works. Now I'm going to add the ping code. The first thing I do is I've made a file to hold the SSID connection parameters to my guest network, so I don't have to enter them directly in the code. I'm going to create a new file. I'm going to call it uping.py. This is going to hold ping code that I got off GitHub. So I'm going to go out to GitHub, and I found this uping that seems to be used by quite a few people. Now I just want to copy that into that uping file I made. So I'm going to do it the easy way. I'm just going to flip over to raw, copy all the code, and paste it into the uping.py file I just made, and we should be ready to go to test it. Now I'm going to add a simple script to test my uping library. You can see it here. I called it test.py. I'm importing the various libraries, so wifiSSID, which has user SSID and the password for connecting to the network, the uping library, and then I'm importing the network library as well to get the network connection set up. I'm going to connect to the Wi-Fi SSID this is fairly typical process for getting the esp32 just to connect to the network. So you see here it's setting up as a station interface, and then it's going to try and connect using the wifiSSID, guest ID and guest password, and it'll continue to do that until it's connected, and then it prints out the information about the network connection. Then I call the uping ping routine, so I give it a target address, the number of times it should ping, the maximum time before it times out from a ping, delay between the pings in milliseconds, whether to suppress the output. I want to see what it's doing as it's doing it, and then the length of the ping. Once that's completed, it'll disconnect from the network. So let's try that out. So first I'm going to upload all my project files. That also does a reboot on the esp32, and then I can just click the run current file to run that current file. It's connecting to the network. It did the 5 pings that I requested and then disconnected again. Just to check that my network emulation is working correctly, just on another machine, I'm going to Bing, or that's a program I set up that uses ICMP packets to check network capabilities from the DOS line. So I'm going to do Bing 192.168.129, which is the Windows 7 PC that I set up with the NEWT network emulator on it. I'll Bing out there, and you see here that it's returning pretty close to my 1000 kilobits per second bandwidth constraint within the. Now I'm going to replicate what I was doing with the Bing command on the Windows command line, but on the esp32. So in my tester script, I've now added 4 ping commands, 2 going to the Windows 7 machine with the NEWT network emulator in it, and 2 loopback pings. They're of varying size, so the first one's always 16 bytes, next one's the maximum of 1500 bytes. Now I'm executing that script, and you see I'm getting 5 pings on the 2 going to the network emulator, 3 to the loopback address, and the information in there, I'm actually going to use the lowest ping times because that's the best case from the 5 ping samples as my actual network latency I'm getting for the different packet sizes. I'm also going to subtract the loopback times because there's going to be some overhead just getting the packet set up for doing the ping before it gets on the network, so they'll give me a more precise number. Okay, so I've got my measurements from my esp32 in my test environment. As you saw, I had measurements for a small ICMP packet, or 3 small ICMP packets going up to the Windows 7 machine running an emulation. It's actually running at 1000 kilobits per second bandwidth emulation. So I did 3 small ICMP pings up there, 3 large ones of 1500 bytes up to that machine and back. And by comparing the time it takes for the differences in network latency between the small packet and the large packet, it tells me how long it takes for the network packets to get onto the wire, get up to the emulating machine and then back down again, which I can then use to calculate the bandwidth as well as the latency between the probe and the target machine. You saw the measurements I got. So for the small packets, I got I use the lowest measurement of the 3, so I take 3 measurements just to make sure I'm not hitting other packets or hitting congestion at the time of the test. So the lowest one will be as well as the network can do, which is kind of what I'm trying to find out. So the first one was it took 9.43 milliseconds at its lowest. I also did pings to the loopback or local address, so really not going out on the network from the esp32, and the shortest one of those was 5.53 milliseconds. And I did that second one just to get a baseline, because there's going to be a certain amount of time the esp32 ping routine takes to load buffers and do things on the actual processor before it sends things across the network. By taking that out of the picture, it gives me a better baseline for what the actual time was on the network, not including esp32 processing time. So there's a size of 36 bytes, and then for the larger one of 1500 bytes I do the same thing. So I get the lowest time going across the network, which was 38 and 1/7. Let's make sure the time's here. 38.17 milliseconds. And again, looking at the time it took the esp32 to prepare to do that was 10.82 milliseconds. So again, higher baseline time just to do the processing of setting up the packets and things, as you'd expect with a larger buffer. Subtract those two, that gives me 27.45 milliseconds. Okay, so this is telling me the difference between this 3.9 milliseconds and the 27.45 milliseconds is the difference in time it took the esp32 to get the larger size packet onto the network. And it's actually a round trip, so it's actually doing it twice, so we'll include that in the calculation as well to get the actual bandwidth. So if I subtract the lowest time, 3.90 milliseconds, from that maximum time, it gives me 23.45 milliseconds. Okay, so that's the difference in ping time on the network due to the differences in packet size. So to calculate the bandwidth, I'm going to divide 1000 milliseconds by 23.45 milliseconds. So that will scale the time up to a second rather than being in 23.45 milliseconds. I'll convert the difference in packet length, so as 1464 was the difference between 36 bytes and 1500 bytes. I'm going to multiply that by 8 to convert it to bits, and then I'm going to multiply by 2 because it's actually doing a round trip, so it's measuring getting the effect of the bandwidth constraints on both trips. And when I multiply all that together, I'll get, and let me get my calculator. So 1000 divided by 23.45 times 1464 times 8 equals, so that's bits per second, one trip, because we're doing the result of the latency was for 2 trips. We multiply that by 2, gives me the one-way latency, so it's 99891 bits per second. And remember, I had the emulator here running at 1000 k bits per second, and that's fairly close to what the numbers should be. I think it's about 2% difference, so it's close enough for doing the network capability measurements. So next video, I'm looking to convert this ping routine into a bing routine, so incorporate all the math that I was doing badly on in freehand into a routine in the actual, what will be called the bing routine.